G'day viewers. In this segment we'll talk about modulation, or how to represent bits as signals. Okay, so here is the setup. You must know this setup quite well by now. We have a computer on the left sending bits to a computer on the right across a link. But of course across the link we can't send bits, literally we send analog signals. So we need to work out some way to represent these bits with signals. I've said that many times. You must be wondering how exactly we do it. That's called modulation, and that's the topic of this lecture. Let's dive right in. Here is a simple modulation scheme. It's the one that you would think of first, I think, if you were just trying to come up with one on your own. We will simply use a high voltage to represent a 1 and a low voltage to represent a 0. This is a modulation scheme called NRZ, for non-return to zero. The name's for archaic reasons, don't worry about it. We can work through an example. You see I have a sequence of bits here, and I'm going to draw the waveform underneath. So for a 0, we have a low voltage down here. Then I'm going to go up to a high voltage for a 1, down to a 0, up for a 1, 1, 1, 1, 0, 1, 0, 0, 0, 0, 0, 1, 0. Oops, looks like I've got a little bit of noise on there. Must be just the way a waveform would look. Let me clean it up so you can see it a little more. There it is. That's one kind of simple modulation. Now there are many other schemes which are variations on this, which can be used in practice. For instance, we could use more than two signal levels to represent bits. If I just look at if we group the bits that we sent, 2 bits at a time, we could send more different levels. If I go over those bits, I think the sequence was 0, 2, 3, 3, 1 from the bits before. If I use 4 signal levels, it would look something like this. This will be 0, this will be, well, level 1, 2, 3, and 4 to represent a 0 through 3. So I'll start low, then I will go up 2 levels, then I will go to the top level, and down to the not quite the lowest level. There we are. That would be using 4 levels. The schemes which are used in practice are very much driven by engineering considerations for how you get this to work. I'm going to talk about one of those considerations, which is called clock recovery. So for clock recovery, here's an example of the problem. Imagine that we have this NRZ signal here. Here it is, a 1, and then a 0, a 0, a 0, a 0, lots of zeros, big long run of zeros. If you are the receiver, you see this signal, but you don't see the bits, of course. Your job is to work out what the bits are. So it's clearly a 1, and then how many zeros is it? After a while it gets very difficult for the receiver to accurately work out the transition points between 1, 0 and the next. We could imagine that you'd have a very accurate clock, but that turns out to be expensive. Instead, what you would really like are frequent transitions in the signal itself so that you could help work out the timing of the signal at the receiver. Now, there are several different ways that you might go about this. In your text, you can look at, there is an example of something they call Manchester coding. That is a coding where there is a transition built into every signal, either a 0 or 1. They all include a transition, a waveform which has a transition. Another approach is something called scrambling. You could exclusive OR your data with a pseudo-random signal, which makes it highly likely that you'll get transitions. You can look at these designs for fun. Instead, what I'm going to do is tell you just about one form of modulation that's used to help with clock recovery. And that's called 4B5B. Now the idea here is that we're going to map every 4 data bits into 5 code bits, which are then sent as a signal. And we'll do this in a way where we won't have long runs of zeros. So here are some examples taken from the table. Here's an input of 4 bits, 0, 0, 0, 0. And if we want to send those 4 data bits, we're instead going to send the 5 code bits, 1, 1, 1, 1, 0. At the receiver, we'll map back from code bits to data bits, so we'll know what we were talking about. There are 16 entries here in the table. They're not shown, they're omitted, but just to save space. But you could imagine there's a whole table full. And if we follow this mapping, you'll find that there are at most 3 zeros you can get in a row. So we won't have long runs of zeros anymore. Great. Of course, if you've been thinking ahead, you realize that you can have fairly long runs of ones. We haven't done anything to prevent long runs of ones. So to prevent that being a problem, we can use a kind of coding where we invert the signal level on a 1 and keep it at the same voltage level for a 0. This form of coding is called NRZI, where the I stands for invert. We invert on 1. And it's also shown in your text. I'll give you an example. And here in our example, I've reproduced the table of 4B, 5B for reference, or just some of it. You can see the message bits I want to send. They start with 1, 1, 1, 1. Okay, let's look that up in our table. You can see over here on the left, that should go to 1, 1, 1, 0, 1. I'll write that in, 1, 1, 1, 0, 1. Next, we have 4 zeros. That goes to 1, 1, 1, 1, 0, 1, 1, 1, 1, 0. And finally, we have 0, 0, 0, 1, which in our table goes to 0, 1, 0, 0, 1. 0, 1, 0, 0, 1. So those are the bits we actually want to send using an NRZI signal. How do I send that signal? Since this signal inverts on a 1 and stays the same as a 0, I'll show that transition in the middle of a bit time here. So if I just arbitrarily start at the bottom for a 1, then the 1 will contain an inversion. And then for the next bit, there's a 1, it's another inversion of the signal level. 1, an inversion. 0, I stay the same. 1, invert, invert, keep on inverting, stay the same for 0, 0, invert on the 1, 0, 0, 0, invert on the 1. And that is the waveform that I would send. I would then be able to see the transitions, get enough transitions at the receiver to find the bit boundaries, and then go back from my code words to my data bits, and everything would be good. I would have sent bits of information across a link. Oh, here's that example for you, just cleaned up a little bit so you can see it better. Now, what I've told you about so far turns out to be what's called baseband modulation, how you would literally send a signal over a wire. That's great, you can do that. When we talk about wireless or fiber though, we want to send information not by putting a signal directly in the medium, but by encoding it on a carrier signal which is operating at a higher frequency. The reason for this is that only higher frequencies are going to pass well through the media, or we might want to divide up the medium in terms of frequency bands to permit multiple people to use it. So we need to work out how to send information on higher frequencies. It might sound a little tricky, modulating a carrier. It's not so bad. Let's see. Here we can work through an example. So first of all, let me show you, this is just the carrier. The carrier is just a signal which is oscillating here at some desired frequency. This could be around 2.4 gigahertz for 8 to 11, for instance. Now to modulate it, we can change it in several ways. We can change the amplitude, that's how far up and down it is. Maybe I should draw here, the amplitude is how far up and down it is. The frequency is how fast it wiggles. We can have it wiggle quickly or a little bit more slowly. And the phase is where it is in its cycle. We could change the phase from up down to maybe down up, would be different phases. Let's see an example. So here is passband modulation, an example of it. At the beginning, I show you the baseband modulation signal. It's just our old NRZ signal. I'm tracing over it just so you can see that it just simply goes from zeros to ones and back as it encodes bits. Now, our first passband modulation is going to modulate the amplitude of a carrier. So you can see here, the carrier is not shown directly, just the modulation is. And you can imagine there's a carrier going up and down just as before, but its amplitude has been changed. Its amplitude is 0 for some of the initial bits here, and then its amplitude is 1 when it's oscillating up and down with that amplitude, with that magnitude. Alternatively, here is another kind of number 2, a different kind of passband modulation, frequency shift keying. You can see now that I oscillate rapidly for a 1, this is a 1, and I oscillate more slowly for a 0. And finally, we have phase shift keying. This signal looks a little more difficult to see, but in essence I'm using a waveform which starts by going up and then down. Although this would occur more rapidly, there would be many cycles in each bit time. That will represent a 1. And a signal that starts by going down and then later up, so it's out of phase with the other signal, will represent a 0. With these schemes, I can now represent information on carrier signals, which are in frequencies of our choice. Real wireless modulation schemes are considerably more complex than I've shown you in these examples. In fact, you can take a whole communications course to understand some of this in detail. Nonetheless, what we've covered gives you the basics of how we send information, bits of information with signals across either wired or wireless links. We'll move on next to error recovery.